Hello, I'm going to walk through the first example of this section. Uh, so it's a maximization problem in this section 4.2 optimization 2. So these are the application problems. When we talk about optimization, optimization 2, we will try to solve real world problem by using the mathematics we learned, especially the derivatives. So the example is a city's metropolitan transit authority operates a subway line from commuters from a certain suburb to the downtown metropolitan area. Okay, so it's subway. Currently, an average of 6,000 passengers a day take the trains and paying a fare of $3 per ride. Okay, so you got 6,000 passengers per day, and everybody just pays $3 for the ticket. The board of MTA, okay, Metropolitan Transit Authority, contemplating raising the fare of the commuting to $3.50 per ride in order to generate a larger revenue. Engage the service of a consulting firm. Okay, so they're not sure whether this increase of the price of fare will result in an increase in the revenue. So they need to ask the consulting firm. And then the firm just did a study, and it reveals that for each 50 cents increase in fare, the ridership will be reduced by an average of 1,000 passengers a day. So if you increase the price of the train or subway, the passengers will drop down. Okay. And then after some study, the consulting firm recommends that MTA stick to the current fare of $3 per ride, which already yields maximum revenue. Okay, so that's the research conclusion. And we need to show that the consultants are correct. So in other words, the MTA should not change the price of the fare. Okay, so how do we do this problem? The first step is to assign some variable for the problem we're trying to solve. So we have the number of passengers change with the price of the fare of the ride. So we have two variables here. When the price changes, the passengers number change. And we can call this price P. So that's per ride. And the total number of passengers, X per day. And then we can also call the total revenue R. Okay, so that's what we're trying to maximize, right? So let's just start this problem by assigning the variables. Okay, so let X denote the number of passengers per day, and P denotes the fare per ride, and R be the MTA's revenue. Okay, so so from the condition of the problem, it says for each 50 cents increase in fare, the ridership will be reduced by average 1,000 passengers. So we can calculate the rate of change. Okay, when the price changes, the passengers number change. So we can calculate the rate of change of passenger with respect to the price. Okay, so the rate of change passenger. So that's the number of passenger number per day. And with respect to the price. Okay, or the fare. And it's what? Okay, so that's for every 50 cents increase in the fare, you're going to reduce the passengers by 1,000. So, so that'll be 1,000 divided by, or negative 1,000 by 0.5. Okay, that's in dollars. So it's negative because you get a reduction of passengers. So that's negative. So that's the rate of change of passenger, with respect to the change of price. Okay. So now currently we have the passenger number 6,000 and the price $3. Okay. So so if we change the price to P, then the passenger number will be changed to X, as we already denoted. So the change of the passenger number will be X minus 6,000. We don't know what X is, but we know the change of the passenger number is X minus 6,000. And because the rate of change of passenger number is with respect to price is negative 2,000. So we can set up an equation. Let me just do it in this way. So we can set up an equation of X minus 6,000 over P minus 3. Okay, so this is the change of passenger number, and this is change of price. The current price is 3. The current passenger number is 6,000. So if we change both P and X, then the new value of P and the new value of X, if you subtract the current price and current number, then that's the change in the price and in the number. So if you divide them, you get the rate of change of the passenger number with respect to the price, right? And that should be equal to negative 2,000, isn't it? Okay, from that, we can, set up an equation. We can simplify this equation to obtain what? So let's see. So we get X minus 6,000 equals negative 2,000 times P minus 3. Okay. Times P minus 3, isn't it? Okay, so that's the equation we get. So we can, simplify this a little bit. So let's just do it step by step. So if we distribute negative 2,000 to P and negative 3, so we get negative 2,000 P plus 6,000, right? Okay. So we can rewrite this equation a little bit if we want. Okay, let me just put it U9 here. So we can rewrite this equation a little bit. So let's just combine like terms. So we can subtract 6,000 both sides. If we do that, we can get x minus 12,000 equals negative 2,000 p. And we can also, rewrite the equation by dividing negative 2,000 on both sides. Okay, and we're going to use this equation later. Okay, so if we divide negative 2,000 on both sides of the equation, we get a p on one side, and the other side will be x over negative 2,000. If you do that, you're going to get a negative 0.00 5x, I believe. Okay, and then plus 0.6, 12,000 over 2,000 is 6, not 6. Okay, so so that's what we get. The next step, we need to calculate the revenue. Okay, so the revenue, or which we assign for the revenue, is equal to x times p. Okay, the number of passengers times the price per ride per passenger. So that's x times this function. So p is negative 0.005x plus 6. So just multiply by that. Okay. So if we distribute the x, we get the negative 0.005x squared. Okay, so plus 6x. All right. Now we need to maximize the revenue. Okay, right? So they want to get maximum revenue. Okay. Okay, so they want to generate a budget revenue. So let's try to find when we can obtain the maximum revenue. But first, we need to find out the interval for x. Okay, x cannot be any number. First, it has to be positive. That's the number of passengers per day. But it also has a maximum number, and that's because when you increase the price, the number of passengers will drop. So at some point, if we increase the price more and more, you're going to get the 0 passenger. There will be no passenger. So there is a number that x cannot be more than that. Okay, so that can be determined from this equation also too. So let's just fix that. So since the price has to be positive, non-negative price. You cannot get a negative price. Okay. You don't pay the person who take the ride. Okay. So that means P is greater than or equal to 0. All right. Is greater than or equal to 0. So that means what? So then what do we get? Then we're going to get this inequality. So this is the P, negative 0.005x plus 6. It has to be greater than or equal to 0. And how do we solve this inequality? It's pretty easy. Okay. So we can move 6 to the right, so it becomes negative. So we got negative 0.005x greater than or equal to negative 6. And then we divide it by negative 0.005 on both sides. So then we can solve the inequality in this way. And remember, when you divide a negative number into inequality, you have to reverse the order. So the greater than or equal to becomes negative, becomes less than or equal to. And on the right side, we got negative 6 divided by negative 0.005. So that's 12,000 if you do that. Okay, so divide by negative 0.005 on both sides of the inequality. We got the x on the left and the 12,000 on the right. Okay, so and then what? So thus x is on the interval from 0 to 12,000, isn't it? Okay, so you cannot exceed 12,000 passengers, but you can, you cannot also have a negative number for the passenger. Okay, so that's the interval for x. Then we just compute the revenue function and find the absolute maximum of the revenue. Okay, so this is the absolute value problem. Just do the same steps as we did before. First, we find the critical numbers for this function. Okay. Let's find the critical numbers of the function or revenue R. So what you do, just take the derivative of R and set equal to 0. Okay. So let's do that. So we get R prime. So R is a function of x, of course. So that's R prime is also a function of x. So R is negative 0.05 squared. So R prime is just negative 0.05 times the derivative of x squared, which is 2x. The derivative of x squared is 2x, as we know. And then the derivative of 6x, which is 6. So then we just simplified. So 2 times 0.0005, which is 0.001. So that's negative. Okay. So the critical number is, we need to set R prime equal to 0. So set first to the equal to 0, that will give you the number. So this is the R prime. Negative 0.001x plus 6. So set that equal to 0, and you can easily solve this equation and to get. Okay, so you can move 6 to the right side. And then divide by 0.0001 or negative 0.001 on both sides. And then we solve the equation. So we got the x equal to what? So divide by negative 0.001 both sides. So we got the x on the left, and on the right we got negative 6 over negative 0.001. So that will be 6,000. Okay, that will be okay. So I guess I wrote too many zeros in here. So that should be right. Okay. So that's the critical number. Then we just compare the revenue function at the critical number. We only get one critical number and the endpoints. So compare the values of R. At the critical numbers, x equals 6,000, x equal to 0, and x equal to 12,000. Okay. Okay, so that's what we need to do. So this is the critical value and the endpoints, x equals 0 and x equal to 12,000. So let's just do that. So R is that. So R equals 0.0005x squared plus 6x. Let's see. So R of 6,000 is 0.5 times, 0.005 times 6,000 x squared, 6,000 squared, okay. Times 6 times 6,000. So what do you get? Okay. 0.0005 times 6,000. I believe we got 3 or negative 3. Negative 3 times 6,000. So that's definitely negative 18,000. 6 times 6,000, so that's 36,000. At the end, we get positive 18,000. So that's the R value at x equal to 6,000. Then we compute R of 0. Okay. So this time is pretty straight. So it just plug in 0 for x in all. So we got 0 everywhere. Okay, so this is 0 squared and 6 times 0. So everything is just 0. All the terms on the right. So the revenue is 0 for x equals 0. And then we can do the same thing for 12,000. X equals 12,000. Then plug in that in R. So we get R of 12,000 equals -0.0005 12,000 squared plus 6 times 12,000 squared. Okay. 12,000, I'm sorry. So 0.005 times 12,000, I think we get 6 or -6. -6 times 12,000. So that's -72,000. And plus 6 times 12,000. That's also 72,000, but positive. Okay. So they cancel completely, so we get 0 here. So if we compare the revenue at those 3 values for x, you can see, the maximum value is 18,000 at x equal to 6,000. So, so that's what is currently the system is making the revenue. So it indeed makes the maximum revenue at the current price and the current number of passengers. Okay, 6,000. Okay, remember, currently it has 6,000 passengers. So they don't need to change the price. Okay. All right. So in order to make the maximum revenue, they just keep the current price and the current passengers number.